You all again. I'm here with a power system operation and control subject for the current semester, and I'm standing before you with Almighty and all those good and well wisher who filled energy in me to stand before you. This is presented to them, and I begin with the content, which is a syllabus, which just I outlined with you. 5 modules of this particular course is put very systematically to make you comfortable to understand power system, its basic interconnection and operational aspects and how it is being done in the real world. That is being put in a systematic way in 5 modules, and it is taking little more than what the prescribed hour. No matter, it can be done in an ease of way. Then let us move with the first interaction. What is electrical power system? Whenever we begin any power system courses, it is quite natural to interact with the candidate or audience. What is the power system? How a structure of the power system be visualized? So this is the power system which is composed of generation setup, transmission setup, sub-transmission, distribution and load, where the generation is centered with the resources. So invariably we define power system is a very complex interconnection of generation, transmission, distribution and variety of load. Power system is put with the objective. It is to fulfill the requirement of the end user. The end users are here loads. Loads might be industries, corporate, offices, schools, domestic users, or any other alternative new and challenging load. Presently, I am using this word because the era is electric. Therefore, new and challenging load. To meet the end user's requirement to the satisfactory level of their choice, it has to perform appropriate generation. Set up generation by the mode of hydro, thermal, nuclear, renewable and other available resources, so that such a generation by capacity is able to meet the requirement of the end user very suitable to their subjected specification. Once it is able to meet the requirement, definitely the one part of the objective of the power system is met. The other part of the objective is, or second objective is, making the balance of active and reactive power, keeping the voltage of the power system buses terminals at specified value is a challenge. And keeping all these in balance and ensuring appropriateness in operation by taking care of all such contingencies like overloading, failure, fault, natural, or any accidental on the given power system. The power system has to cope up, overcome and stand well with all these possibilities such that it can meet the requirement of the end user very effectively. This is the complex interconnection of all these resources. Therefore, that figure number 1 is just a simple interconnection of generation to the load, and another diagram at the right side show you symbolically a generating setup, a generator, a transformer, transmission line, sub-transmission, distribution and reaching to the end user is outlined. Similar to that, one simple single line diagram I have drawn, which is showing a generator, a transformer, bus and circuit breaker and outlined specific loads, etc. This is just to make you what is electrical power system. This is just a distribution line over here. Likewise, power system is designed with the objective of generating adequate megawatt and megavolt ampere to meet the end user satisfaction and to keep the resources optimally utilized. This is another great challenge on the power system operation, which is whichever is the resource it is making use of, hydro, thermal, which may be coal or oil, or gas, or any other renewable energy resources which it is making use of. It should see to it that effective operation of generation or generator must be planned so that the usage of resource is so optimal to meet the requirement which is contingent and keep the reserve for the future use. It should not be consumed because the resource is in abundance and I should consume. I should plan for the next day's load, which is surely a dynamic in nature. That is being the economic operation or economics connected to the operation of the power system. Then moving to the next slide, whatever the discussion just now I was interacting with you, the power system is just an interconnection of generation system, transmission, distribution, load, etc. Load may be any kind of load, a variable load, static load, or any other specific by way. It has to be met by the system in an appropriate manner. To do that, operation becomes very necessary. Then, while operating, the adequacy of the system, state of health of power system has to be monitored. As the loads are changing, do the current system able to cope up with that? Or it calls for the installation of additional generator, additional infrastructure, switchgear, etc. and so on. So it has to be appropriately planned so that such a plan makes the things possible. And I was interacting with you all by or in meeting all these objectives. Definitely, power system encounter lot of difficulties in the heading fault. It has to be very proof of such fault, able to protect itself and able to keep working even after ensuring the fault or encountering the fault. We call it as fault tolerant system. For that, a proper study, we call it as a power flow, has to be done frequently. And short circuit study analysis, adequacy of the controllers and circuit breakers and isolating mechanisms and their behavior timely and all have to be checked periodically and kept in line. Then all these together has to be a part of the operation. Then we have a simple one graph which is showing a station, a power system's load. How is that load on the power system keep varying? This is one of the old data picked from one of the textbook Wood and Uhlenberg, which is a demand on the station compared to an example of 1998 and 2000. In a 2 years of span, how is that load on the station gradually increased on the hour of a day? It means this is the load curve on the station has to be appropriately addressed by the generation setup. Whether it is a simple single generating setup, generating and meeting the demand, or there are such several generating stations, hydro by mode, thermal coal by mode, or natural gas by alternative, which are put together, put in parallel to meet a certain demand would be a case. This is just to show you how task on the power system is put to meet this demand effectively. The generation has to address this particular variation in the load hourly. So this example show you how the power system engineer, which we call them as dispatcher. When I go down the screen, you will come to know an energy control center is a computer control of energy generation or power generation, which always keep on putting a task on the generator. How much would be the set point on this generator, on another generator, and how to route the power, what is the best and optimal way to route the power has to be worked out. In that due regard, the exact load plus the losses plus the contingent variation what would occur in the due course of meeting up of the demand has to be properly viewed and addressed by the dispatcher. So that while doing so, he must or she must keep an eye on economy of the operation. So this is simple outline. How is that load curve on the station is viewed? This is a pattern. How is that load growth take place? Here you will find growth in load. Similarly, I have how a power system is viewed. What are all the characteristics of a power system? How it must be designed then. This is how. One, it must supply power practically to everywhere, to the every consumer of their needs. It means it is such a way interconnected with a number of generators by type or by capacity. It is able to meet the demand of every user interconnected to. And it must supply power to customer at all the times. This is called continuity of service. Intermittency shall be avoided. It means the consumer who is connected should ensure continuity of delivery without any break or discontinuity. This must be one of the objectives of the power system, and it must be able to supply ever-changing load demand at all the times. See, this is very critical. The load is static for hours, say morning for 4 hours. In the midday, in the afternoon, load is suddenly shooting up. And again in the evening, it is falling. Again in the mid, it is rising. Something that trend you can imagine. Power system must be capable of making this demand notice, able to cope up with its generation such that this particular pattern of demand is addressed all the time in over a day of your observation. This is very critical because it's being very dynamic in nature. Appropriate management has to happen here. That must be the expectation from the power system. And the power supply should be of good quality. So when I say power quality, definitely it comes with the voltage level. Specification of voltage, certain voltage kV or V, what we speak about, it should be within the permissible range of operation. If you go back to one example for this, every equipment in the power system interconnected or loads which are interconnected are sensitive to the voltage. Any change in the voltage beyond a certain percentage, plus or minus the tolerances, it is sure to have mal-operation of that equipment or a component. On whose information, if your connected circuitry is dependent, definitely the wrong signal, wrong set point, wrong operation will definitely cascade it into next, protrude into next stage and make the system go adverse. Therefore, the equipment and all the connected mechanisms which are sensitive to the voltage should be properly nurtured. So, we should keep in eye or keep on eye the voltage quality, the voltage level and magnitude and harmonics, the switching harmonic level, distortions what the power system is going to ensure off and on due to the switching or due to the switch off of the particular component. It has to be maintained within the toleration or tolerance limit. Else, the components which are connected are sure to suffer. Now, if you could see another view of it, when we have electrical power system, electrical components like a generator, transformer, any other electrical machine, in which we have eddy current and hysteresis loss components. Definitely, the sinusoidal nature of the wave matter more there. If the distortions are so large, the shape of the sinusoid which deteriorate to an extent will definitely affect those components which are functioning, unnecessarily get overheated, unduly absorb higher power, pulsations, abnormal torques are exerted on that. That will lead to disorders or failure of components or malfunctioning and disconnection, anything like that. It means to say the quality of the power which we are supplying to the end user has to be maintained very good to the specifications specified. That is the main objective of the power system itself. The power supply should be economical. This is another great requirement from the customer perspective, where whatever we supply shall not be which is non-reachable. Whatever we speak about quality supply, continuity of supply, meeting up of end users' requirements and to all the connected users should be affordable. It should be available to the reachable periphery so that people can connect and get connected to and pay for which what they have used. So it should be economical in nature. So from this, when we say a power system has to be operated by interconnecting several generators with a transmission mechanism, proper switch gear and sub-transmission, transmission, and over distribution, and to meet the end user in a proper fashion. While doing so, definitely some of the aspects come into picture like frequency. The system frequency must be kept in and around the specified, say example 50 Hertz in our continent. So what will happen if the frequency variation goes beyond certain plus or minus 0.05 Hertz? Definitely it's going to create torsion, vibration, and increase the losses in the machines which are interconnected to the system. Similarly, the voltage magnitude which I was speaking about, they must be maintained well within the tolerances specified. Otherwise, the components are sure to malfunction and deteriorate in their performance. So these two factors are frequency and voltages are very seriously considered for our operation. Then, exactly what will happen if the fluctuation in the frequency, which is detrimental, which is an adverse phenomenon on the power system itself. Key to the phenomena, the fluctuation in the frequency from the power system side. That is due to the load itself. The loads are causing the change in frequency or fluctuations or flicker that is affecting the system, and system is trying to cope up with that variation. If that is not addressed appropriately, the effect of which is detrimental to the entire equipment connected to that. They start absorbing higher power and start heating up, create vibration, and they are the other adverse effects we can see. Three-phase AC motors run at speeds that are directly proportional to the frequency. That is going to affect the speed of the AC motors. Definitely the performance of them deteriorates. And if there is a closed loop control system, they start hunting around that steady state stability point of which unnecessarily. Then blades of steam turbine and water turbine are designed to operate at a particular speed. As I say, frequency in turn connected to the RPM of the shaft of the turbine. So that starts making a change in speed, cause for the change in valve open, close, etc. So this is how the effect of that flicker or fluctuation is on input of the input to the turbine itself. Then we have another important aspect of frequency flicker or fluctuation is frequency errors may produce havoc in digital storage and retrieval processes, because the information for the operation of power system is taken from lot of interconnected devices which are measuring the values and telemetering it from the remote point to the energy control center, in which the frequency is definite to cause havoc and cause some change in the information and also affect the retrieval process. Hence, it is detrimental and we have to maintain a good frequency aspect. Now, coming to that a small step towards, how is that power system state is monitored? What we were seeing is power system is an interconnection of generation setup, transmission, distribution, and load. It's put with the objective, it has to meet and address the requirement appropriately. While doing it, it definitely encounters so many dynamics, which is a changing load or a fault or any failure or any minor variation, anything for maintenance, anything may be the reason. There is a situation called out of service, partial in service, like that. Then, in general, entire power system, when we view, states of power system becomes very cautious. The first state of power system is normal, alert, emergency, extreme emergency, restorative, and to the normal. So, when we have a normal state, imagine there is an interconnected power system with a generator, a transmission mechanism, and adequate switch gate, and transformers, end users, etc. So, every connected equipment in the power system, generator, transformer, and loadability of the transmission line, everything is intact. No component is violating its capacity limit. When I say limit, every equipment has its rated capacity and ability to sustain certain overloads, plus or minus tolerances around its working point. So, such an equipment is scheduled to generate certain megawatt, load certain MVA with the transformer, deliver certain MVA on a transmission line to a load, etc. So, all those equipments are said to be functioning normal, very safe, and there is no overrun, overloading, deviation in the operating point of every equipment which is found safe. We call it as normal. Normal is one of the states where every equipment is intact, interconnected, functioning very well within their specified secure ranges of points. Suppose a load change or any fault or any disturbances in the system might cause the system to change its operating point to a minor extent. It is not that every equipment will change its operating point. It may be a minor change in a transformer's load. A load center demanding little additional load and transformer is subjected to deliver a higher load. Or a transmission line is loaded a little higher than what right now it is set. But it is not going beyond its max capacity. What is the operating load right now plus a certain increase is allowed. It means a small shift in operating point is noticed. So it is just a switching. It may be a switching, it may be a removal, it may be a turn off of any load. Anything may be a reason. A minor change in operating point is observed. But system is intact, system is interconnected to one another. And it is just a notice. System can be brought back to the normal by correcting that contingent variation that we call it an alert system. So, if I do not control that parameter change, it may enter to emergency. It means alert is a very simple state where equality and inequality. If I think of these keywords, equality means the capacity constraint, terminal voltage rating, and its output capacity rating. And inequality are min and max limits of that particular component. We call them as equality and inequality constraint. So everything was intact when it was a normal. When it comes to the alert, a minor variation is noticed, but it is not threatening the component. It is not causing the overrun, failure, overloading. A minor change is noticed on that, which is a very safe operating point for the component, but as such interconnected operation is considered a minor noticeable change for you, which you can correct and bring back to normal. But suppose if you do not do it, such several components may present such scenarios. It may be one transformer right now. Over 10 minutes, another transformer adds up to this similar case. It becomes two transformers in alert state, like three transformers, one generator, two transmission lines. Like this, number of components may find themselves making a noticeable change in their operating point, which is expected. So this, if I ignore, it will lead to an emergency, which is a noticeable change, which will make surely there is an overrun and crossing of its inequality limits, min and max values, which is a threatening, which if I do not take appropriate care, system may lose that particular component. It means to say a transmission line, excessive power flow is noticed. It is an alert, a healthy capacity of which is say 10 MVA. You are drawing 6 MVA from that, 10 and 6. It is able to carry, but for you permitted is 6. A 7 MVA is flowing on that. It is a capacity of that line is not threatened, but operating point wise, your values are changing. In that, if you allow it to go, let us go, then such overflows or such overruns will be in number that will enter into emergency. Several such components running with the alert without any correction may lead to emergency, and there could be a failure of component over here. Therefore, it must be seen that emergency control mechanisms are different. When it is in alert, it is simple correction. Simple set point changes will bring it back to normal, but when the system enters from normal to emergency, simple things will not work because it has to become normal. To become normal, there must be either the cause of that contingency has to be eliminated. It may be one reason. There could be an excessive overloading of a particular transmission line that is causing due to fault. It may be. There may be a load growth directly that is unexpected. Then unless and until you curtail that, you eliminate or reduce that load, your operating point of control may not come back. Therefore, it is called controlled load curtailment can be the way. I can reduce it, I can bring back the mechanism. Or I can definitely make fast valving or make them isolated such that the system integration is maintained. If I fail to do it, what may happen? System is still intact. System is under your control. But you notice some of the components are overburdened. But they are running your requirement. They are carrying your load, but they are burdened. They might fail if you do not take care. That is called extreme emergency. The wrong set points done, wrong decisions taken during the emergency, which you would have controlled properly due to the wrong set point, wrong mechanism, wrong judgment, which will lead to several component failure in part or in full, which we call it a cascaded failure. Interruption of the delivery is guaranteed. Here, when it was an emergency, there was no interruption. System was intact, delivering your requirement. But you notice there is an increased threat on the system. It is just like a patient in the observation. So patient's fever is increasing in gradual mode. The medication or prescription which is being provided is okay. Let's observe for another 4 hours, another 4 hours. But still then, even it is increasing tremendously uncontrolled, I cannot keep watching it. My methods to control it must be very different. That's called, when it is in a simple observation, how it can be brought back. If it is a noticeable change, it's a different method to control it. If I still keep the old technique to control the emergency situation, surely I will lose the control of my component. That is called as extreme emergency, wherein the particular component is out of your operation, but several may go in a due course of time. Interruption is highly noticed, and load shedding is guaranteed. You cannot deliver the load because you have no generation or you have no transmission lines to deliver the power, or there is no control available on that. So, inadequate control measures exercised on the emergency mode will lead to extreme emergency, which a separation we have to. Cascading failure or interruption, load shedding is possible. I'm quite sure in this state of power system, extreme emergency, disconnection is noticed. Failure of component is noticed in full or part. There is no integrated complete system in shape. Part of the system may be functioning in either only generation or only load or part of generation load mixed. Think of geographical disaster, a natural earthquake or flood situation where an islanding situation is resulting. A generating station is intact, generation is going on, but there is no one to deliver the power because no transmission line, broken transmission line, or transmission receiving station has totally gone out of your control, damaged due to disaster like that. So that is not receiving the power, how can you distribute? Or generators have drawn away in the flood. Definitely there is no generation at all, but there is a load, there is a transformer mechanism, or there is a substation available. Likewise, islanding is possible. That is due to the wrong set points, wrong practices, wrong judgments on emergency state of system conclude extreme emergency. Then to recover back, it is a restorative phase. Restorative phase is a phase which is recovering from the existing part of the power system after being affected either simple or badly. So during this state, it is a recovery What is there, try to connect it. What is being met, at least to keep continuing. In that way, recollect, reconnect, and make the things compatible to one another and make the system recovered in part and full slowly, so that restorative phase is just a recollection, reconnection, and getting back to a normalization process. Once it has come back from restoration, 100% sure there is no original system. Originality of the system is totally lost either in fraction or in major part. But system can be regained back to normal in space of time. So this is how states of power system is viewed as normal, alert, emergency, extreme emergency, restorative, and back to normal. Similarly, the same slide I have with me with a different perspective. You can see here, normal, alert, emergency, in extremity, and restorative phase, and normal. This looks very comfortable transition mechanism, which makes a sense. When it is a normal, how it enters to the alert. The dotted line shows the control action. I can bring it back to normal by picking control action. And from the alert, you can just see inadequate things will lead to emergency, wrong judgment lead to extremities, and in the alert itself, the author has projected another dotted line here. It may enter very bad shape if you just ignore it without ensuring what may happen. So this is how it may enter, and restorative phase, it may go normal or it may come to alert and it may go to normal later. This is how all these things are possible. The alert state is just generation shifting, increased reserve, emergency may be fault clearing, generation tripping, load curtailment, or in extremis, wherein extremely disconnection is noticed. Load shedding, controlled separation, operation back to one has to be done. So this one slide presents you back the states of operation of power system, which will definitely make a sense that observation of a patient in an ICU, how the recovery of the patient from a particular pain or suffering is brought back to the normal by having proper diagnosis, proper testimonials, proper medical implements or impact on the person, how it is bringing back to the normal, similar to which a power system has to be felt, the states of which definitely make it to normal. Then I come to the objective of the power system again. Now we define what is a power system, why power system is interconnected to meet the requirement, what are the challenges which it will encounter. Now I am in a very clear position to magnify the objectives of the power system and control. The objective of the power system control strategy is to generate and distribute power in an interconnected system as economically and reliably as possible while maintaining the frequency, voltage within permissible limits. Changes in real power mainly affect the system frequency. So just view this paragraphic objective, which is exactly mean generate adequate active and reactive power to the end user's requirements, maintaining the voltage and frequency as specified. As we are very much aware, power systems behavior, very peculiar behavior, P, Q, V, and delta or F, in which we have a very specific interconnection of P active power with the frequency, P and frequency, Q and voltage, means reactive voltage, they are very sensitively connected. There is a connection between them, there is an interconnection between them, very strong interdependency among them is noticed. This is called uncoupled or decoupled view of the power system. Therefore, whenever there is a shortfall or a mismatch of active power, it will definitely affect the frequency. I have to set up frequency controlling. I have to set up generation otherwise. If there is a voltage flicker or a fluctuation, it indicates that system is suffering with the reactive power generation. There is no sufficient reactive power in the system, which is indicated by a change in voltage. Therefore, I have to tackle reactive power. That's the reason the objective of the power system is to maintain or generate adequate P and Q to the requirement of the load, maintaining the V and F constant. That is how it is being outlined. So this is how a simple objective is put into. Then to meet this, definitely a block diagram which makes you a sense. I have a block diagram which show you so many information. A generating unit at a rectangular dotted block, which is having a generation setup, a generator, which is having a prime mover control, and it is coupled to a generator. When the prime mover is a turbine, to which we have a input flow control, either it's a water or a steam or a gas, whatever it is the control. Then it is going to get the input fuel and it will drive the generator, and generator generates electricity which is taken as a output voltage and which is monitored by the excitation system, which will control the field pole supply. Field supply is managed by excitation system. Then there is another clause. We will see it in another terms again. Then speed of which is fed back to the primer to open the valve appropriately. For this, the stimulus is so many inputs. What is the schedule of the generator? What is the requirement of the frequency? What is the tie line flow interconnected from this generator to the next stage? What is the demand of the system? All together decide what is the set point of input to this. Then it will drive the generator. Generator generates and is connected to transmission grid and it is going to deliver the load. This is how a requirement schedule the control of input fuel that will generate or drive the generator, monitored and controlled, and it will give out the power to the required. This is how various controls in a power system can be viewed in a single diagram. And as in this diagram, if the system starts functioning appropriately, it is sure to encounter these many challenges. The one is stability aspect, security aspect, reliability aspects are the great challenges that the system will ensure. When I operate the power system appropriately, I'm quite sure always I'm encountering challenges. I have to solve a problem, next one, they are continuous in turn. I have to encounter and work out, overcome and manage such that my integration of the system remains intact. So therefore, these are the challenges that the system is going to ensure and encounter. So in the next class, again we go ahead with this objective and I move with the further slides, key concepts and further interaction. Okay, right now I'll stop over here and I will hand over to the next class teacher.